Hello everyone, my name is Members Griffin, and I'll be taking you through our project, our right, the right for our project, which is Trustworthy uh, Intelligent Simulator for forecasting tourism demand. We are two authors, me and Mr. Wire Crispus Ben, and so let me take you through. Uh, First of all, let me take you through the background and introduction. The overview of tourism. As you know, tourism is a key contributor to global and local economies, driving GDP, job creation, and infrastructure development. GDP is a gross domestic product, I think, and that's like an income a country earns from abroad, I think. Then the vulnerability of tourism is that it is sensitive to economical shifts, political instabilities, environmental changes, and global events, making accurate forecasting essential. There's a need for making a real-time and accurate forecasting, considering these vulnerabilities, like the factors which affect tourism. So, the objectives of this uh, project is to develop an intelligent AI simulator, like create a system using machine learning and simulation that can accurately forecast tourism demand of both global and local economies. The adaptability is to design the system to adjust to various scenarios, providing reliable insights for stakeholders to make informed decisions in a dynamic environment. The computational problem statement, the challenges are that traditional models struggle with complex interactions among influencing factors. Yeah, like the factors which influence tourism, the demand for tourism, which include in political instabilities, bad weather, so which I had mentioned above, like the existing models struggle with uh, interacting all the factors together. And inaccurate prediction can lead to poor decision making and financial loss for stakeholders. So that's why there's a need for effective resource allocation, strategic marketing, and infrastructure development to rely on precise demand forecasts. So the current limitations that are available are these limited and validated timeless data, that's difficult in capturing influence of other factors on tourism and financial predictions. Those are the traditional methods, the limitations that are occurring. And then there's also data complexity. There's difficulty in learning the underlying patterns in the multivariate data sets. Or these data sets that we are going to use have they have a lot of variables. And so uh, to obtain the patterns in these data sets is also a limitation. And also there's need for precision enhancing predictions. What we propose, like our solution, is to develop an artificial intelligence simulator using machine learning and simulation techniques. The key features here, we are going to have multivariate data analysis, scenario analysis for events, and real-time predictions via APIs. The forecasting methods, we are going to use ARIMA and SALIMA. These are time series forecasting models that generate patterns and will be able to help us forecast in our project. Then we also have random forest and gradient boosting machine learning models. All those will be used for forecasting and predicting and making precise predictions. Uh-huh. The simulation environment will be built using AnyLogic for scenario analysis and impact assessment. Here we shall be bringing in different scenarios, changing and bringing in more variables at different levels, positive and negative, to analyze and assess the impact of what can happen to the demand of tourism. And then the evaluation metrics are MEA, and then root mean squared, and also a DF. So the proposed solutions and novel contributions. This is what I'm just from telling you. Just it's a continuation. Then use of productive model, predictive model. This is how our model will be able to predict for what the scenarios that can happen. So we are going to use material perceptron MLOP regression, and then also support vector regressions. Those will be used for predictive modeling. Then we also have adaptability. This is for real-time updates, what is happening in real time. And we are going to use the Kalman filter. The evaluation matrix, I had told you already, the ADF, and they will be explained later. The novel contributions we are going to make within this project that we are going to drop XAI techniques for model transparency and interpretability. Then we are going to do an advanced forecasting. We are going to do advanced forecasting models using ARIMA, SALIMA, random forest, and then gradient boosting. Then we are also going to create an intelligent AI simulator for forecasting tourism demand. Then we are also going to create a simulation environment for scenario analysis, that is for impact assessment. And then there's also we are going to create an accessible API for seamless integration and distribution. So visualization and methodology. The methodological framework, we have flowcharts from data collections to forecasting. And then the key steps that we shall follow is data preprocessing, then EDA, which is exploratory data analysis, then model training, evaluation, and deployment. Then during the EDA, we did data cleaning, which was filling in the missing values, if leaving out the unnecessary values. And then we did feature engineering, adding in more features, extracting more features from the features that are provided to make features that are helpful to our project. Then we also added aggregations to as part of feature engineering, where we did total trips per year, average trips per purpose, total trips per region, monthly trends, quarter analysis. All those aggregations, all those are the features that we're able to extract from the data we had. And so there are many that we did, but these are like the top 5. So all this is to generate a trend and categorize the variables. So we did interaction analysis. We did seasonal trends, also comparative analysis, and also we did lagging features from all the data that we did from the data set we had to create a more wide data that we'll be able to use to train our model. So for data visualization, we plotted time series plot. That one is to visualize the trend over time, to detect seasonality, and also to observe any anomalies, I think, in tourism. Also, we did a time series decomposition. This is to split the data into 3 components: trend, seasonability, and the noise. This is for better understanding of the underlying factors that affect tourism and demand separated, to know that this factor uh, affects tourism alone, and this factor affects demand alone, so that you can know how you can be able to integrate them. Then also did rolling averages, that is to smooth out short-term fluctuations and highlight long-term trends in tourism. Because the data set we used had data from 1998 up to 2016. So we had smoothen out fluctuations, small fluctuations, and also see the trends within the long-term trends within the tourism, within the demand. So we also did qualitative analysis. This was to determine which variables have the most significant impact on the tourism data, like some strong variables, like for example, we had is it political instability? That's how it affects the tourism demand. Like, so if a place is full of war, of course, no tourists won't go there. So though we had to determine the variables that are more significant, and we value them. Also, we did a box plot for categorical variables. This is to show the distributions of tourism demand across different categories, such as month, days of the week, types of tourists. Is it leisure? Have they come for business? Have they come for vacation? So all that is what we did for data visualization. And these are the graphs that we are able to plot for data visualization. That's the time series plot, the time series decomposition, rolling averages, box plot for categorical variables. All those we did in visualization, and I've already told you why we are doing it. So modeling, this is how we are going to model our project. First of all, we'll get raw data, then we do data pre-processing. Then we already did all this. We have already done, of course. We've already done EDA, yeah, the exploited data analysis, which I explained above. Then we propose the data. Then we are doing model training. This which we are doing. This is the stage we are on. We are training models, different models. After that, we shall go for hyperparameter tuning. We shall go for model evaluation, and when the models don't perform as we expect, then we shall do hyperparameter tuning until the models perform as we expect. Then after that, we do explainability and model selection. Then after that, we shall put in the simulator, like I told you, to simulate to assess the impact of the different variables. Then we shall then put it up for user design development. That's why and then we shall develop an API, and then we shall deploy our model. So the results, these are the results. So we use two data sets. Like my fellow colleague will explain about the first data set. Let me explain about the second, because I worked most especially with the second data set. So I used the ADF metrics, like the augmented Dickey Fuller. It's a statistical test used to determine whether a given time series is stationary or has a unit root. So this in case non-stationary. If it's stationary, then if it has a unit root, then it's non-stationary. So the null hypothesis of the ADF tests that the time series has a unit. That's the null hypothesis, or it's non-stationary. While the alternative hypothesis, H1 says that there is a series of stationary. So a more negative value indicates that there is a strong evidence against the null hypothesis, and vice versa. Okay, like if it's a more negative, of course, there's a strong evidence, and ours was negative 21.111, meaning it indicates that there is a strong evidence that we should reject the null hypothesis, and we go with the stationality. So I think I will further explain about stationality in the coming video. And okay, like it's a way of assessing permanent trends. Like if it's stationary, meaning if a trend happens, it's likely to happen, meaning it's a stationary trend. And for non-stationary, it means that it happened and again it didn't happen. Like it's not a trend. So if ours had a very strong stationary, meaning we are just working on improving it to make it better. And then the p-value, it implies that there is a very low probability of observing the current data if the null hypothesis were true, meaning if it was something bigger than this, meaning it would be a higher probability of observing the data within our current stationary. Yet, so ours had 0.0, meaning there's no probability, there's no chance of observing the data. Yet we have a stationary hypothesis, the non-null hypothesis. So those are the results, and then the rest are the references that we use. I think that's it. Thank you.